YouTube? You just got clickbaited. You came here to watch me ski and instead you're getting classical mechanics. Okay, anyways, so the problem is a ski or a mass M is on a frictionless, initially horizontal ramp, so like this. And if it's horizontal, there's no imbalance in the forces, so it doesn't move. So at t equals 0, the incline starts increasing at an angular velocity omega. So it turns into this, or the incline is slowly getting steeper and steeper as time progresses. So the question is, what is x of t, where x of t is the distance between the bottom of the ramp here and the position of m. So the hypotenuse, given that the initial conditions is x of 0 is x naught, so here the distance between m and the bottom of the ramp versus are at t equals 0, and it's not moving initially. So given that this is classical mechanics, we're going to be using either Lagrangians or Hamiltonians. And I'll be using Lagrangians because that's my preferred technique and it's much easier. Okay, you already know what the problem is. Let me just erase this now. First of all, we know Lagrangian is kinetic energy T minus potential energy. So we know kinetic energy has two components, T, or I'll just name it K translational plus K rotational. So the translational is just the box sliding down the ramp. So we know that kinetic energy K is equal to 1/2 mv squared. Our v is going to be in terms of x of t. Since the motion is downhill, it's just going to be 1/2 mx prime squared. Pretty easy. So that's translational. Now, our rotational kinetic energy, it's going to be 1/2 m. And then since the box is traveling this way, because of the fact that the ramp is increasing, then that's going to be 1/2 mv tangential velocity squared. So we know that v tangential is equal to radius times angular velocity. But what is our radius? Well, our radius is x, so our tangential is x omega, making our k rotational equal to 1/2 m omega squared x squared. Okay, so then that would make our t equal to 1/2 m x prime squared plus 1/2 m omega squared x squared. So our u is just going to be gravitational potential energy. So let me just get rid of this. So there's no other source of potential energy. There's no springs or anything like that. It's just gravitational potential energy. We know that that's mgh. Now we need to find h, since that's a variable of time. So what is h? Well, as you know, if you spin this thing around 360 degrees, you get a circle. And circular motion, the x and y component, so if you just draw any vector here, it can be broken down in its x and y components, and the x component is going to be r cosine theta, and the y component is going to be r sine theta. So we know that spinning a vector around the unit, or a unit vector around a circle, if it stays at the same rate, then its height or its y value can be modeled with sine theta. So we know our r is x, so we get mgx sine theta. But what is sine theta? Well, theta is a function of t because it's increasing, and since we know that displacement is equal to velocity, initial velocity, velocity times time plus initial displacement, and that would mean that angular displacement is equal to angular velocity times time plus initial position. So since there's no initial position for theta, since it's on a horizontal ramp initially, we would get mg x sine omega t. So then our Lagrangian, which now I can just get rid of this now because we can figure everything out. That means our Lagrangian is equal to 1/2 mx prime squared plus 1/2 m omega squared x squared. Let me get rid of this now. You guys don't need it because you guys understand it, I'm sure. Minus the potential energy, so minus mg x sine omega t. Okay, so now we can use Euler-Lagrange equations. So here, since we just have x as our only variable, we can put it as, or x is the only variable that we really need to use because we're solving for x. So our Euler-Lagrange equation is the partial derivative of Lagrangian with respect to x equals the time derivative of the Lagrangian's partial derivative with respect to x prime. You can verify the algebra for that one, but it works, trust me. So we can do the math. So this would mean that taking the partial derivative of this with respect to x, you'll get 0 because this term goes to 0 since there's no x in it, plus we do the power rule. These two are constants, so we just get 1/2 x squared. Take the derivative, that's just x, so we get m omega squared x minus, you could just differentiate the x, so we get this as a remainder, equals, well, differentiate with respect to x prime, that's just m, or rather the d dt of m x prime, since that's 2 times 1/2, and then take out the 2 here. So then that's equal to m x double prime, since we're just differentiating x prime. So then we get m omega squared x minus mg sine omega t equals m x double prime. We can cancel out the m's. So now we have, and I'll just do a bit of more algebra. I'll subtract both sides by omega squared x. So we get x double prime, sorry, that doesn't look good, minus omega squared equals negative g sine omega t. Okay, you can slow down a bit if this is a bit tricky, but I'm going to keep going now. You just pause if you want, but I'm going to proceed. So now we just solve for x. So x double prime minus omega squared x equals negative g sine omega t. So we know that from differential equations, I have a video on this, x of t will be composed of a undetermined coefficient solution, so I'll just put a sine omega t. The undetermined coefficients tells us that we have to have a constant a multiplied by whatever form we have here, whatever function form we have, which is sine of omega t. We'll plug this in here, but there's also the homogeneous solutions. So I'll just put x homogeneous. And the homogeneous solutions, when you plug them into the left side, they add up to 0, so they don't affect anything when you plug a sine as well, because you'll just get a sine plus 0 when plugging this in, so it doesn't matter. So, okay, so first of all, let's start off with the homogeneous solution. So we'll set a solution equal to a sine omega t. So we can plug this into the differential equation. So doing the calculus, it's elementary. You'll get a negative a omega squared sine omega t minus omega squared. So a again times omega squared sine omega t equals negative g sine omega t. So now we can cancel out the signs. So we get negative 2a omega squared equals negative g. So then a would end up being g over 2 omega squared. So we now know what our undetermined coefficient solution is, but we still need to find the homogeneous. Man, I'm so good at pronouncing things. Okay, so our homogeneous solutions, well, we can use the method of characteristic equations. So we have x double prime minus omega squared x. We can set that to 0. So we would say that this equates to r squared minus omega squared times 1 equals 0. And then we would say r, obviously r is just equal to plus or minus omega, right? Nothing too interesting here. So then our solutions would come in the form of c1 e to the omega t, and we would get c2 e to the negative omega t. So then our whole solution would end up being, or our general solution is g over 2 omega squared sine omega t plus c1 e to the omega t power plus c2 e to the negative omega t power. But we're not done here. There's a specific solution since there are initial conditions. So you may remember that the initial conditions are x of 0 equals x naught and x prime of 0 equals 0, right? So we need to solve for those. So let's go ahead and do that. So we have this here. We'll say that x of 0 is equal to, we can just plug 0 into t for now. We get g, whatever. This ends up being, the left term ends up being 0 because you plug 0 into sine and you get 0. Plus c1 e to the 0 power. So that just turns out being 1. Same thing here, 0. So you just end up with c1 plus c2 equals x naught. Okay, so then we get x prime of 0. So x prime of 0, that's going to be g over 2 omega cosine omega t plus c1 omega e to the omega t power minus c2 omega e to the omega t power. But then we have to plug in the 0. So let me just do that here. You get 0 here, 0 up here, 0 up here. Okay, so we differentiated and then plugged in 0. So we get 1 here, so g over 2 omega plus c1 omega minus c2 omega. And then that is equal to 0. So now this may look a bit confusing at first, but then you remember that it's just a simple system of equations. So we would say c1 plus c2 equals x naught. So then that means that c2 is equal to x naught minus c1, right? So we can plug this in here. So g over 2 omega plus c1 omega minus this. So x naught minus c1 omega equals 0. So then g over 2 omega plus 2 c1 omega minus x naught omega equals 0. So then here we would find that doing the algebra, c1 is equal to, subtract that by both sides, so we get 1 over 2 omega times x naught omega minus g over 2 omega. So we can just simplify this out here. Let me just draw an arrow to indicate that this is the sequence of steps. It looks a bit confusing, so then we get 1/2 x naught minus 1/4, or we get g over 4 omega squared. So then we got that. Now we need to solve for c2. So we remember that c2 is just x naught minus this, so we end up getting c2 is equal to x naught minus this, 1/2 x naught minus g over 4 omega squared. Then this ends up being positive 1/2 x naught plus g over 4 omega squared. Okay, so now that we have that solved for, then we know that what our full solution is then. It's x of t equals g over 2 omega squared sine omega t plus this 1/2 x naught minus g over 4 omega squared times e to the omega t plus 1/2 x naught plus g over 4 omega squared e to the negative omega t. That's our final solution to our problem. Yeah, simple problems can be this complicated. Anyhow, if you want to continue watching me ski, I think I'll add a clip of me skiing at the end of this video. Thank you for watching.